Today we're going to start chapter 3, which is about compounds and molecules. So a compound is a combination of elements that are chemically combined, and molecules, instead of atoms like an element has, their particles are now called molecules because they're not made out of just one thing. Okay, so we have a couple different kinds of compounds. One of them is an ionic compound, and an ionic compound is made out of a metal and a nonmetal, if you remember cations and anions. In other words, these are made out of ions. These are elements that had to give up electrons or gain electrons in order to form a bond. Okay, so anytime you put a metal and a nonmetal together, you're going to get what they call an ionic bond. In other words, one of them gains electrons, one of them loses electrons. The ultimate goal in forming a bond is to make sure they get 8. 8 is the magic number. If they have 8 in their outside, then they're stable. So in order to do that, some elements will give up electrons. Like if they only have 1 or 2 on the outside, they'll give up those 1 or 2, and then you go down to the next level and they'll have 8. Or if you have like a nonmetal with 6 or 7, they'll pick up 1 or 2 and then they'll have 8. But because now they don't have the same number of protons or protons and electrons like they did before, now they have a different number of electrons. If they lose them, they become positive. That's a cation. If they gain them, they become negative. That's an anion. Okay, most ionic compounds are called salts. And again, you can tell if you put a metal and a nonmetal together, you're going to have a salt. Okay, an ion formed from a single atom is called a monatomic, mono meaning one, ion. And then there's polyatomic ions. If you remember this, if you had chemistry before, polyatomic ions are like a molecule with a charge, like phosphate, sulfate, nitrate, acetate, all those guys. Remember, they're like sulfate is SO4. It's 4 oxygen and 1 sulfur. They're held together, but in order to be stable, they have to have extra electrons, so they have a charge, a -2. So they could either gain 1 electron, and there's only 2 of those, hydronium and ammonium, or they can lose 1 electron, 2 electron, they can gain, I should say, electrons so that they'll have a negative charge, and that would be like nitrate, sulfate, all those other, if you remember your polyatomic ions. If they have a -3, like phosphate. If they have a -2, like sulfate. If they have a -1, like nitrate. Okay, so in other words, they had to gain electrons to be stable. So they call them, they're like basically a molecule with a charge. So they're called a polyatomic ion. Poly meaning many, many atoms. Okay, each polyatomic ion has a unique name, its formula, and its charge. This formula tells you what's in it, what elements and how much, and then the charge is going to be like -2. That tells you it had to pick up 2 electrons. Okay. All right. Oh, sorry about this. This just all popped up. Okay, an ionic compound definitely has a ratio. Okay, it always has to be the cations, anions. The lowest ratio makes up an electronically neutral. So again, the cations and anions charge have to equal each other. If the cation is +2, the anion has to be -2. Okay, so when you're writing the name for it, I always told you, if you've had me before, you crisscross them. Okay, like if you have iron that's F2 and you have oxygen that's -2, well, since they're both the same, you don't have to worry about them. It's FeO. But if you have iron that's +3 and oxygen that's -2, you'd put a 2 by the iron and a 3 by the oxygen. You crisscross them. Okay, you always list the cation first. The metals always goes first, and then the non-metal always goes second. Okay, and again, the name of the first one you leave alone, the second one you change the ending to IDE. Okay, so MgCl2, Mg is magnesium instead of chlorine, chloride. And I'll have a chart in this that has the ion names, so make sure you download that. It's really handy when you're naming compounds. Okay, K2CO3, okay, I have 3 capital letters so that I know there's a polyatomic ion, so I look up CO3, and that's carbonate. So this would just be potassium carbonate. Okay, Ca is calcium, SO4, polyatomic ion, sulfate. Okay. Now these ones, iron can be 2 or 3. So I have to look up which one it is. Well, if phosphate's -3, then iron must be +3. So this would be iron 3 phosphate. This one, NH4, is ammonium. Don't write nitrogen, hydrogen, please. Ammonium, and then Br is brome instead of bromine, bromide. Okay, CuO, copper, is another one of those. On that chart that I'll have you run off, you'll see if they have a split box. Copper can either be 1 or 2. Okay, well, oxygen's -2, so the copper must be +2. So it'd be copper 2 oxide. Notice that this is never here. Okay, don't put the Roman numeral as a subscript. I used to tell my high school kids if they did that, I'd shoot them in the face. Okay. Okay, formulas. All what you do for formulas is you write the symbols, you put the charges, and then you crisscross them. Okay. So like sodium is +1, oxygen's -2. Since they don't equal each other, I put a 2 over here. Now I have +2 and -2. If it's a 1, you guys don't have to write it. Okay. Aluminum is 3, Al plus 3. Carbonate is CO3 and it's -2. So I'm going to put a 2 by the aluminum and I'm going to put the carbonate in parentheses and put a 3 by it. Okay. Now, whenever you have a polyatomic ion and you need more than one, make sure you put it in parentheses, because if I just wrote CO3 and then put another 3, it would look like CO33. I do not need 33 oxygen. I need 3 carbonate groups. And now if you look at the charge, carbonate's -2, -2 times 3, -6. Oxygen +3 times 2, +6. So they equal each other. So if you just crisscross the charges, they're going to balance out. And again, if they equal each other, you don't have to write anything. Okay, if this was 2 and this was 2, you just write AlCl3. But they're not. They don't equal each other, so crisscross them, and now they will equal each other. Gold 3 chloride, this is its charge. So Au plus 3. Chlorine is Cl and it's -1. So I'd crisscross the 3. And again, remember this 3 is not here. It's on the other side. Okay? All right. That was ionic compounds. Now, covalent compounds are a little different. What happens with a covalent compound, instead of transferring electrons where one gains and one loses, they share electrons. This is going to happen when you put 2 nonmetals together. If you put carbon and oxygen or hydrogen or whatever, those guys together, they won't give up their electrons. They won't take in electrons. Instead, they share their electrons. So they stick together. Like an ion is just going to be sodium with a +1, one individual. When you have a compound, with molecules, you can have bunches of them. If you think of like DNA as this huge molecule, but they all stick together, okay? So a molecule is a distinct entity, okay? It's not a lattice like a crystal. It's composed of 2 or more nonmetals and they're held together. They stick together to get their 8, okay? And so now you can have like 2 stuck together. You can have 2 million stuck together. It just depends on the compound, okay? Most covalent molecules are assembled from carbon is pretty much going to be your base, okay? And hydrogen is common. Carbon and hydrogen are the 2 most common. But again, nitrogen, oxygen, phosphorus, and sulfur. And if you remember from last chapter, those were the things that make up all living things. The most common, the 6 most common elements in living things: carbon, hydrogen, nitrogen, oxygen, and phosphorus, and sulfur. They're the ones that make up your covalent compounds, your covalent molecules. Okay? All right? Covalent molecules can be found in all 3 states of matter at room temperature. In other words, you have some covalent compounds that are solids at room temperature, like sugar. You have some that are liquids, like propane, and you have some that are gases, like, I said propane. Propane is a gas. Sorry, you guys. What would be one that would be a liquid? Methanol, okay? And then propane would be a gas. Got to get my head straight here. Sorry. Okay. So when we're talking about covalent compounds, the nonmetal atoms achieve, and the only way they can get a full valence electron, and when I say full valence electron, I mean 8. That's an octet, they call it. The only way they can get that is by sharing electrons. Okay. So a shared pair of electrons is a single covalent bond. One from one part, one from the other. And they put them together, and then you got a bond. Okay. Shared electrons are in an orbital around both the nuclei, so they share them between the 2. Okay, the distance between the 2 nuclei is called the bond length. The shorter the bond length, the stronger the bond. Okay, if you think of it like as a pencil, if you have a little short pencil and you try to break it, it's hard. If you have a long pencil, it's easy. So if the bond length is long, the distance between the 2 nuclei is long, then it's easy to break that bond. If it's short, it's really hard. So a molecule has lower potential energy than the separate atoms. The reason why they join together, it makes them much more stable. Okay, sorry these don't come in one at a time. I was having a little trouble with this PowerPoint. Anyway, a covalent molecule is composed of molecules with the same unique composition. Okay, so they're together, they're very unique, and then you're going to have these molecules. They're all going to be the same molecules, and they're going to have unique properties because of that. The molecular formula tells you what atom you have, And then it also tells you what, it'll have a little subscript, a little number down below that'll tell you how much. Here it says each atom type in alphabetical order. So if you have a compound like sugar is C12H22O11. Okay, there's 12 carbon, there's 22 hydrogen, and there's 11 oxygen. You put them together, and that's what a molecule of sugar is. Okay, the molecular formula cannot be altered without changing the identity of. If you take off a couple hydrogen, it's no longer sugar, it's something else. Okay, all right. So a binary compound can be named by using a simple set of rules. Okay, now we're talking about molecular compounds, not ionic. When we did ionic, we just left the name of the first one alone, calcium. The second one we named as, the change the ending to IDE. When you do molecular compounds, what you do is you have these rules, mono, di, tri, tetra, whatever. And these tell you how many of a substance you have. Okay, so the first element, you write the name as it is. If there's more than one, you put a prefix. So if it was like C2, you'd write dicarbon. Okay, the name stays the same, but you put a prefix. If there isn't more than one, you just write carbon. Okay, the second one, you change the ending to IDE like we did before. And again, they have to have a prefix. So if there's only one, you use mono. But if there's, like if it was C2H6, it would be dicarbon hexahydride. Okay, so you use kind of part of the, like you did with the ionic, but with ionic you never have to worry about using dis and tris. The reason for that is you use the charges to balance them out. When you do these guys, there's no worried about writing out the charges or whatever. The name tells you everything. Okay, it's all there. Dog. Oh, sorry. All right, so molecular compounds between two nonmetals is a different naming system than an ionic. Okay, so name the following. Two ends, that'd be dinitrogen, trioxide. Okay, I'm telling you everything that's in there. Okay, and again with these, you can put them together. You can drop the O. There's all kinds of different ways, but I just leave them in there because I need to know that they're in there. Okay, Si is silicon. There's only one, so it'd just be silicon. 4 chlorine, that would be tetrachloride. Not chlorine, but chloride. Okay, and CO, carbon, and then the second one has to have a prefix. So if there's only one, you use mono. So carbon monoxide. I'm sure you guys have heard of that one before. Okay. All right. So when you're doing a Lewis structure, what do we got here? We've got 12. Okay. I got 2 minutes left here. All right. So when you're doing a Lewis structure, Lewis was a guy that worked with the electrons. That was his thing. So he would write compounds and he would actually show where the electrons came from. Okay. So like here, carbon has 4. How do I know carbon has 4? Look what column it's in. The A columns. It's 4A. It has 4 electrons that it needs. Well, if it has 4, it needs 4 more because remember, it needs 8. Hydrogen is unique. Hydrogen only needs 2. Everybody else needs 8, but hydrogen only needs 2. So what you do is you situate them. So 1 from hydrogen, 1 from carbon, and so on all the way around. And then when you get here, you can, instead of writing it like this, you can put a dash is 2 dots. This represents a bond, a bond, a bond. Now if you look, 2, 4, 6, 8 for carbon, and then each of the hydrogen have 2. So now you have a stable compound. This is called methane. Okay, it's natural gas. Okay, some atoms share 4 electrons to get their octet. In other words, if you don't have enough electrons available, you might have to form like what they call a double bond, where you share 4 electrons, or you might have to do a triple bond. Okay, if you do carbon dioxide, you actually have to have carbon in the middle, and it puts its 2 carbons, and then the oxygen puts in, so you have a double bond on each side. Okay, so that, and then sometimes in order to get it, you have to have a triple bond. Okay, you have to share 6. For some reason though, there's not a quadruple bond. Okay, there's only a single bond, which is 2 electrons, a double bond, which is 4 electrons, and a triple bond, which is a 6. Okay, if you look at group 5, which is nitrogen in everybody, 6, which is oxygen in everybody, and 7, which is all the halogens, chlorine, bromine, iodine, they don't share their valence electrons. Okay, so they have non-bonding pairs. You can see it down here where it talks about it, but I'm going to run out of time. So we'll quit right there and we'll talk more about this next time.